Hello, my name is Molly Wrobleski, and I am team lead for the Hobart Filler Metals Senior Design Team. My teammates are Brooke Sokowski, Leo Sauter, and Catherine Houston, and our project studies the effect of cerium on sensitization and weld strength of 5000 series aluminum alloys. So 5000 series aluminum alloys make up roughly 60% of Hobart's aluminum filler wire market. These alloys are high strength, so they are typically used in structural applications like marine, automotive, and construction. The primary strengthening mechanism for 5000 series aluminum is solid solution strengthening through magnesium alloying. This is because magnesium atoms can replace aluminum atoms in the metal's atomic matrix, which creates strengthening distortions in the lattice. Upon rapid cooling, such as you would see in welding, magnesium exists in a supersaturated solution. Most 5000 series alloys contain around 4 to 5% magnesium, but the solubility of magnesium in aluminum is only around 1%. This means that when heat is applied to the alloy, it provides enough energy for magnesium to diffuse inwards towards the grain boundaries and form the beta aluminum 3 magnesium 2 phase. This process is called sensitization. Electrochemical differences between the beta phase and aluminum matrix establish galvanic cells, causing intergranular corrosion that eventually propagates into cracks and compromises the integrity of the welded part. One way to reduce sensitization is by using an alloy with a lower magnesium content. However, this comes at the cost of the alloy's strength. Our challenge for this project is to reduce sensitization in these alloys while still maintaining their strength. We approach this problem by creating a new 5000 series alloy with other alloying additions. We chose cerium as our elemental addition due to its tendency to form stable, incoherent aluminum cerium metallics when introduced into aluminum alloy systems. Given all of this, our formal hypothesis is that if cerium is added to a 5000 series alloy, then intergranular corrosion will be reduced because aluminum cerium intermetallics will interrupt the continuity of the beta phase and block the continuous corrosion pathways through the material. We tested our hypothesis by creating a center point DOE with varying magnesium and cerium levels. These were compared to a baseline alloy with no added cerium. The values shown in the table show the results we got from compositional analysis after casting. Our approach to this experiment centered on finding a quick way to develop our alloy and weld it. Traditional wire manufacturing is a long and intensive process, requiring many cycles of drawing and annealing. Our group decided to extrude our wire instead of drawing it, which significantly cut down on processing times. Our processing route included casting aluminum ingots into a permanent mold, machining them into billets, and extruding them into 3mm wire. We created the welds using wire arc additive manufacturing. This technique is an additive process similar to 3D printing, in which the material is added layer by layer to create a solid product. The picture on the left shows our welder here at MTU, and the schematic on the right shows how it creates wall-like welded structures. Test samples were machined from the center of the weld using electrical discharge machining. In total, we got 5 tensile bars, 3 corrosion coupons, and 1 metallographic mount for each alloy. Preliminary data from tensile testing has found that 4 out of the 5 of our alloys did not have a significantly different tensile strength from the base, with only the 3 magnesium 2 cerium alloy being lower. However, we have only tested some of our samples, so more data will be needed to verify this. We also looked at our intermetallic formation using electron microscopy. We overlaid a backscattered image taken from the same field of view on the top, which shows individual grains as different colors. What we found is there are areas where the intermetallics form both along and across the grain boundaries, such as these 2 regions pictured here. Finally, for sensitization testing, we'll use a method called nitric acid mass loss testing. We will weigh samples, immerse them in nitric acid for 24 hours, then weigh them again. The acid attacks the beta phase preferentially, so the mass loss per surface area indicates the degree to which samples are sensitized. At the time of this video, our samples are currently being sensitized in the furnace. Future steps in the project will be performing the NAMELT testing and then seeing if the corrosion results correlate with the quantity of intermetallics that we found during microscopy. Our team would like to thank the following individuals for their contributions to the project. We couldn't have done this without their support, and we have greatly appreciated being able to learn from them throughout the process. Thank you.